Okay. Daisy is in Washington. Tyler, Rachel, Michaela. Zach is not. Yeah, he is. Just wearing a hat. Andrew, Colby. Okay, I don't see Christy. I wonder if she might be still sick. All right. We are going to continue talking about motion. We're going to talk about acceleration today and accelerated motion. So I have a picture here of a car that is going from, what does V stand for? Okay. Velocity, if it has an arrow over the top. If it doesn't, then it's speed. Right, so there's that dichotomy. So this here, technically, that's saying speed. But we have the direction shown by the arrow, so I could have put the arrow over it, and then it would have been velocity. You don't need a direction if it's zero. You know why? Yeah, there's no direction to define if it's zero. Yeah, so with or without the arrow doesn't really matter. If it's zero, it's just zero. And if it's accelerating, the velocity changes. And so that was going 0 to 20 in 5 seconds. It's changing velocity. So what does a car's speedometer measure? And remember, this is clicker channel 33. And let's see, among these people, if you look at your back of your clicker, can somebody tell me who says 6676D for your ID? The ones that I see with no ID are Zach and Denford. That's yours, Zach? Thank you. You feeling better, Daisy? Or not Daisy, Christy?
Yeah, I do.
Good. And you did much better in the homework after I sent you the email. So who is 66B3E? Is that yours, Christy?
That's me.
That's. I thought you said that yours was 66760.
Oh, sorry. I'm the 60.
Joe, you're B3E?
No, 66760. I'm B3E.
Okay. I wanted to put scores in yesterday for the clickers, and I realized that people would probably be really annoyed if they had zeros and they've been answering, so I figured I'd wait until I can get these, lined up. Okay, so now, if you're going to answer, you better have answered by now. We have our answers here, 3 and 5. Okay, now all of these had to do with how fast you're traveling. What's the difference in speed and velocity? Okay, velocity has direction, speed doesn't. So nobody said velocity. That's good, because the speedometer doesn't tell you what direction you're going. So then it just comes down to, is it the average speed or is it the instantaneous speed? And in this class, all of your test questions are going to be multiple choice or true and false. Those are bad for this kind of thing because in reality, depending on your explanation, I would accept either one of those answers. Why? Because about 15 years ago, some scientists made a big stink about the fact that there's really no such thing as a pure instant. We only have very small time differences. And so that means there can't be anything instantaneous. Your speedometer is essentially measuring the average speed for an extremely small amount of time. Now, we tend to call that the instantaneous speed. So you could technically argue either one of those. It's not the average over a large amount of time, though. It's over a very short amount of time. So typically, we would have said the instantaneous speed was correct. So if this was on a test, that would have been the one that would be considered correct, but then I would feel angst because, well, a person could have, meant the right thing with the other answer. And it's always bad to have questions where a person can mean the right thing and choose a different answer, right? I hope you agree with me on that test theory. Otherwise, you basically are teaching a coin flipping class. Okay, so the speedometer just tells you how fast you're going, and here it says at a given instant in time. Move right past that. Which quantity is the highway patrol more interested in? You can answer now. I didn't have it up there. Is he more interested in your average speed or your instantaneous speed? This is, of course, based on the assumption that he wants to take away your money, because, well, that's my general feeling on this. Okay, we got one more now. 66B62. Who's 66B62? Okay, so that would be Denford. All right. Now I have a clicker for everybody in the class. Okay. 7 people said the instantaneous speed. Let me stop it so we don't have people say, oh, I want to be with the majority. 2 people said the average speed. Typically, I would say the instantaneous speed. If they catch you going, depends on where you are. If you're in California, if they catch you going more than 10 to 20 miles an hour over the speed limit, they'll give you a speeding ticket. Depending on the freeway, speed limit's 55 almost everywhere. We always do 80, right? You guys, anyone here from California besides me? No, okay. But they're going to take your money. If they can find you going over the speed limit, they don't care how long you were going over the speed limit. You were doing 50 in a 30 zone. I don't care if it was for 2 seconds. So they're more interested in that instantaneous speed. Now, when they check your speed by aircraft, one of the typical ways they do that is they just paint 2 stripes on the ground, and the airplane's flying overhead and says, took that guy this long to go from one stripe to the next. Now, if they're measuring the time it takes you to go from one stripe to the next, what are they measuring? Your average speed. So in that case, they're measuring the average speed. They can be pretty sure that unless you're speeding up or slowing down, it's pretty accurate. If you sped up and slowed down, at some point you're actually going faster than that, so they still know if your average speed is this, you had to have gone at least that speed or higher. But instantaneous speed is what the ticket's all about. My radar gun had a highest number of, 87. Unfortunately for you, the speed limit was 20. In that case, you're in trouble. Okay, velocity versus speed. We've talked about this multiple times. Velocity has direction, speed doesn't. Things that have direction we call vectors. So velocity is a vector. Anything that's a vector has both a magnitude. What does this term magnitude mean? Right, if you don't know the meaning of the words, me saying the words doesn't help you. So what does that term magnitude mean? Okay, what it means is the size. So I could have, for that opening slide, it started with a magnitude of 0, right? Speed was 0. It ended with a magnitude of 20 meters per second. The magnitude is how big it is. Notice the units are part of that magnitude. It's not just the pure number, it's the number with the units. And then we have the direction. So a vector might be 20 meters per second east. It has the direction specified and the magnitude to 20 meters per second. Or I could say my home is, 3/4 of a mile, that's a magnitude, in a direction that's, 20 degrees south of east from here. There I've specified a direction. That makes it a vector. Direction and magnitude. So velocity isn't our only vector. We can have distances as vectors or as scalars. Right before I just said my house is 3/4 of a mile away. I mean, I did point before, but I didn't give a direction with it. I just pointed. If I say my house is 3/4 miles away, is that a scalar or a vector? Okay, I haven't used the word scalar, have I? Scalar is the opposite of vector. A scalar only has the magnitude. So if I say my house is 3/4 of a mile away, that's just a scalar. By the way, scalar is spelled with 2 A's. I have seen people spell it like something that is going to scale, as C-A-L-E-R, but it's not that. So a scalar has only magnitude, whereas the vector has both the magnitude and direction. So both the scalar and the vector have magnitude, but the vector adds direction. Okay, that's a lot of talking for just that simple thing of the difference in a vector and a scalar. Now a question for you. A car goes around a curve at a constant speed. So here it has a speed v1, here it has a speed v2, and those are equal. I'm sorry, you can't answer yet because I have to hit a button on the computer. I forgot that this was a clicker question. I was going to explain it without giving you that chance. Now you can answer. So is the car's velocity changing or not in this case? Okay. We had 7 said yes, the velocity is changing, and 2 said no. Well, there's a majority, pretty clear majority. Somebody who said yes. Why did you say yes, the velocity is changing? Okay, Denford.
Because the direction is changing.
That's right. The direction is changing, and velocity is not just the magnitude, not just the speed, it's the speed with the direction. So because the direction changed, it had to be accelerating. And we'll learn later the acceleration when it's going a circle is toward the center. We use the symbol A for acceleration. So the acceleration was changing direction as it went around the circle, constantly accelerating toward the center. Now, our lab on Monday is going to focus on graphs. So I have a bunch of graph things here that I went forward on the wrong thing. Should have gone forward on this. I have a bunch of graph things coming up, but they're not next because I went forward on the wrong thing. Because I'm a genius. For something to change its velocity, it always requires a force. Force is a new term. I haven't used it yet in this class. A lot of people know what force is, you know. I can force you to come to class, but I can't force you to learn. Right? Same idea as you can force it. Bring a horse to water, but you can't make him drink. Okay. Force in physics is anything that pushes or pulls. So I am offended by Tyler's shirt. So I could come and try to pull that shirt off of him. Sweatshirt. And the color scheme. I mean, even the shoes are part of the offensive scheme. I'll have you know, I used to love to wear navy, and then the Broncos changed their colors, so navy became one of their colors. And then I had to purge my wardrobe. Now my wife is trying to change my wardrobe from something besides just silver and black. So you'll see me wearing lots of different colors. It's only because my wife makes me. She is actively trying to get rid of my silver and black clothing. Can you believe that? It doesn't seem like it's an appropriate thing to do. It's a point of contention. That and if vaccines are good for you. So, a force is anything that pushes or pulls. If I try to pull that shirt off, that's a force. If I come and I punch him because he's wearing a Broncos shirt, not only does that make me a bad person, but that would also be applying a force to him because I'd be pushing on him. Now, if I punch him, if I push on him, he's also pushing back on me. So I'd be putting a force on him, he'd be putting a force on me. We'll learn later about Newton's laws, and that's Newton's third law that says, that's the song, well, for every action there's an equal and opposite reaction. That action means force. So you put a force, A puts force on B, B always puts a force on A that's equal in opposite direction. But that's something we'll talk about in later chapters. Right now, it takes a force, something pushing or pulling, to change the acceleration. So if a car is going in a circle, the acceleration is toward the center to make it change directions, and there has to be something pushing it to make it go in a circle. What pushes a car to make it go in a circle when you turn the wheel?
What do you mean? The motors?
Okay, I heard there the tires. I heard what do I mean. I'll go with the what do I mean and then come back. When you're driving down the road in a straight line, you could have a constant velocity, right? Constant speed, constant direction. But when you start turning, you're changing direction. Hence, you have to be changing changing velocity. You have an acceleration. Because an acceleration is the rate at which velocity is changing. So we have to have an acceleration, a rate at which velocity is changing if we're changing direction. And that means we have to have a force, something that's pushing the car to make it change directions. And so we had an answer from Andrew that said the tires. Now, more specifically, it's actually the ground on the tires. We have what we call friction, a force that keeps the tires from sliding. And it's that friction that's putting a force on the tires to push the car to make it turn. That's kind of like foreshadowing for the next chapter or something like that. Okay, I am not even going to spend time on instantaneous velocity. I think it's pretty clear that instantaneous velocity is like instantaneous speed, but it has direction. So acceleration, talking now specifically about acceleration. Our bodies can't feel velocity. In fact, there is no experiment you can do if you're in a closed room with no windows to determine what speed you're doing. You could be stationary, you could go 50 miles an hour. If you're not accelerating, there's no experiment you can do. But there are experiments you can do to tell you about your change in velocity, the acceleration. And so we'll see the next picture. The next slide is really just kind of a goofy slide to say we have an acceleration detector built into our body. So I'll leave it to the slide instead of say what it is. But notice, because acceleration, that's not how you spell acceleration. Back up, and back the bus all the way up. Somehow I'm on the wrong layer. I know you guys don't even know what I'm doing with the tablet, but I have different layers of writing. So if I'm on the right layer, which I'm on now, I can't erase the stuff that's on there. I can write stuff, and I'll just erase that stuff I wrote. Didn't have it set up right because I set up a slide earlier before class. Okay, so getting back to this. Acceleration is equal to the change in velocity divided by the change in time. We learned the word rate. We could have said it's the rate at which velocity is changing. This is all written out in words. Why do I write it in words? Because I want you to understand it. But you also probably recall that I said physicists tend to be lazy. We want to write things the shortest way, not a long way. So we have symbols. So what symbol stands for acceleration? I mentioned it earlier in this lecture. It's the obvious one. A. So we put A. Now, is acceleration a vector or a scalar? It can be both, but intrinsically it's a vector, right? Acceleration has direction because velocity has direction. So I'm going to put the arrow over the top to indicate that I'm putting the vector acceleration is equal to, what did we use to write change in? Delta. So I'm going to put on top a delta and on bottom a delta because I have a change in on both top and bottom. And then what was our symbol for velocity? V with the arrow. And the symbol for time was the obvious T. Time doesn't have a direction. What do we call a quantity without a direction? A scalar. So time is a scalar. There's the short way of writing the exact same equation that's above. I always write it this short way because it takes a lot less time. And to me, it means exactly the same thing. You're learning, you need to learn to read the lowercase, the blue one, and from reading that blue one, know that it says the words that are written above. Any questions about that? Okay, real quick question. What symbol do we use for position? We usually use X for position. What is the definition of velocity? It is the speed with direction, but we have an equation. Now, on the test, you'll have all the equations given to you, but understanding what they mean is really important. And so that's why I'm asking these questions. So an equation, what's the words for the equation to define velocity? Okay, change in position, so that's going to be delta x over delta t. Now, if I write it like this, it's mathematically wrong. Because the left side is a vector, the right side's not. How do I fix that? Actually, I just put the arrow over the x. Now both sides are vectors, it's fixed. Now, you can never have a vector in a denominator. And you can't multiply vectors. You can't take vector x times vector v. That doesn't work out. We do have things like cross products and dot products, but you can't just multiply them. So that's our definition of the velocity. Now we have the definition of acceleration is the change in velocity divided by the change in time. Now from this first equation, we can solve this for position. We can solve for how far something's going to travel if it has a constant velocity. What equation do I get if I solve this upper equation for delta x? I worked through the math of it last class period, just to make sure. I am very sure that you guys can do this. How do I get delta x by itself in this equation? Okay, I multiply both sides by delta t. So if I multiply both sides by delta t, on the left side, I'm going to have v delta t. Now I changed it from the left side to the right side. The other side, delta x over delta t multiplied by delta t. What happens to the delta t's? They cancel, and I'm just left with this. So the distance vector is equal to the velocity vector multiplied by the change in time. But truthfully, for this to be correct, this was the average velocity, and this needs to be the average velocity. I didn't put average there, but if the velocity is changing, then this only applies to instantaneous velocity where delta t is approximately 0, very small time. So my change in position is the average velocity multiplied by the change in time. Now, when you're doing problems right now, they're all going to be one-dimensional. What that means is the motion's only going to be in one direction. If the motion's only in one direction, we usually drop the vector signs. We just say it's a scalar. and positive means to the right, negative means to the left. So for right now, you're going to be working with this problem as x is equal to v average multiplied by the change in time. Notice I wrote it now without the arrows, which makes it not a vector. How do textbooks clarify the difference? I've been using these arrows a lot, right? Textbooks usually just use bold for a vector and not bold for a scalar, which can be confusing. It would be extra confusing if I tried to write it that way, because how would you know the difference in my handwriting for a bold versus a non-bold? So this is what you're actually going to be using right now. So we can calculate the position if we know the average speed and the change in time if it's going in one direction. Likewise, if I take this and solve it for the change in velocity, what's the change in velocity going to equal? It'd be what? That's right. Or dropping the vector signs, because we're going to be doing things as scalars right now. The change in speed is equal to the acceleration magnitude, delta t, for one dimension. Now notice this second equation, the one in green, is change in speed. That's final speed plus or minus initial speed. Delta is always final minus initial. I was trying to think one step ahead. We can actually take this equation there I've written it out. Delta is final minus initial, so delta V means V final minus V initial. And I could say, what is the average velocity? How does average relate to V final and V initial? How do I find the average between two numbers? Add them in, divide by 2. Right, Denford did this for us last class period, right? So it's going to be V final plus V initial divided by 2. That's the average. Why am I going to do that? Because I want to be able to put that and find the position if something's accelerating. So V average is V final plus V initial over 2. And if I take this equation and solve it for V final is V initial plus acceleration delta t. Right, that's taking the V initial and just adding it to both sides. And now I'm going to substitute that. Too many arrows. Actually, that's fine. I'm just going to change color. Okay, so I'm going to substitute that blue in for V final, and I'll have that. And of course I can simplify that because I have V initial plus V initial. What's V initial plus V initial? 2 V initial. And then divided by 2. So it's 2 V initial plus A delta t all over 2. It's all over 2. I can actually break this up and just put over 2 under both of them. And so V average is equal to 2 divided by 2 is most clearly 1. V initial plus 1/2 A delta t. And then I will put this V average into the equation up here for x. So I'll go back to red just so it matches the color before. X equals V average delta t equals V initial plus 1/2 A delta t multiplied by delta t, which is the initial delta t plus 1/2 A delta t quantity squared. This is a very important equation. It's a very nice box. It's a very important equation in what we're going to be doing coming up. This tells us how the position of something changes with time if it has a constant acceleration. Now, your textbook has this equation, except it's missing this term. Your textbook, I'm going to rewrite the equation up here with just the beginning and ending. Your textbook has this equation, but it's missing this term. The reason the textbook has the equation missing that term is because we often like to choose a problem where it starts from rest. If it starts from rest, that means it's not moving, so what is the initial speed? 0. The subscript I means initial, the subscript F means final. So if it starts from a 0 speed, then that term is just 0 that's in the black, and that's why the textbook shows the equation without it. So it's always correct to have the equation the way I have it. The way the textbook has it is only correct if it starts at rest. Now, one thing you note here. Oh, actually, there's another thing I need to point out. The textbook doesn't show the deltas. The textbook actually has, I'll write it with the first term. The textbook has it written just with this. Why no delta, you ask? Why don't we just start our problem at time 0? Right? Well, it'd be kind of ridiculous to say, okay, so I'm going to sit here and hold the ball, and then at 3 seconds I'm going to drop it, and how far has it fallen at 4 seconds? Why don't I just say I'm going to hold the ball and drop it, how far has it fallen in 1 second? It makes more sense to start the timer when I drop it. And so that's a convention we use in physics. So we just say initial time is 0. So delta t is final time minus initial time, or final time minus 0. And so by convention, we write the equation this way. Now, I've done a lot to explain, okay, so here's the equation. Here's where it comes from. Of course, how these equations are useful is what we care about. Right? Once again, on the test, you're always going to have the equations. It's being able to understand them and use them that you're going to be tested over. Okay, this is that silly one. It's a picture from the textbook. We have something that tells us about acceleration. When you fall, your stomach feels a flutter, right? You go on a roller coaster, one of those roller coasters where it takes you up here, and then you sit there for somewhere between 5 and 29 seconds, it seems, and then all of a sudden you fall down. And when you fall, it certainly feels like your stomach is coming up, right? Not necessarily the food, but your stomach feels like it's coming up in you. Right? That's what they're saying. We can detect acceleration in our bodies. You can't actually detect the speed. Now, if you have air blowing by, you can use that. But if you're in a closed room with no windows, so you don't have air blowing by and you can't see out the window, you can't determine speed. But if you change your velocity, if you change direction or change speed, you can feel it. Okay, I have already talked about most of this here. Acceleration, when you say the word acceleration, you're usually talking about a car. And what does it mean to accelerate in your car? To speed up, to move faster. Your speedometer is telling you how fast you're traveling. If you accelerate, your speedometer goes up. How fast you're traveling is changing, and that's the acceleration. But acceleration isn't just speeding up. What else would be an example of an acceleration? Doing what? Not just going backward. Slowing down. Or, you could be stopped going backward and speeding up going backward. So slowing down is also a change in velocity. So that's also an acceleration. Oftentimes people like to use the term decelerate, which means an acceleration in the direction opposite to the velocity. Personally, I try not to use the word decelerate because I think it's just adding an additional complexity. Because deceleration is an acceleration, just in the opposite direction of velocity. So why don't we just call it an acceleration and be done with it? There's one more thing that's an acceleration when you're driving your car. We've already talked about it. What's the one more thing that's an acceleration? Yeah, I'll see his hand motion. When you change direction, since acceleration is change in velocity divided by change in time, if you change direction with your car, that's also changing your velocity, so that's acceleration. So, speeding up, slowing down, that's a G, this is a D. See, I'm not dyslexic, my brain just doesn't go as fast as my hand, and so I put the letters that I'm thinking in my head. Slowing down and changing direction. All of these are examples of what? Okay, those of your education students, they teach you, or at least they taught me, well nigh 30 years ago, I should never ask a question that way. I should have said, what are these? Because they call it a whiplash question when you make it like a statement and turn it to a question at the end. The problem there is the student's mind is thinking, okay, he's going to make a declaration, and all of a sudden you make it into a question, and then the mind has to scramble for, okay, so what was the question? So, what are these an example of? These are all accelerations. So on your car, you have things that will affect the car's driving that will accelerate the car. What things do you have on a car that will make the car accelerate? So Michaela said, the accelerator. Denford said, the steering wheel. And Rachel, it is just EL, right? I wrote Rachel. Said the brakes. Wow. My brain is there. We have some evidence. Okay, now, those are indeed the three things that I would consider accelerator. You said the gear shift. Well, the gear shift changed the transmission, and so it will make things different, but I generally just consider these three. The accelerator we often call the gas pedal. And actually, instead of brakes, I should have put the brake pedal, because those are the controls we use. So we have three controls that will accelerate the car. We tend to call the gas pedal the accelerator because it's giving us an acceleration in the direction we're going. The brake pedal gives us an acceleration in the opposite direction we're going, what some people call a deceleration. And the steering wheel changes the direction, which is an acceleration that is perpendicular to the direction you're traveling. So one accelerator is forward, one is to the side, and one is to the rear. All right. I've already talked about everything on that slide and everything on that slide. I have mentioned the acceleration is toward the center when you're going in a circle. This picture is trying to illustrate that. So we start with the car over here with its velocity pointing up and to the left. We end with it here going down and to the left. The equation for acceleration is delta v over delta t, which would be, in this case, the final v2 minus the initial v1 over delta t. I have these velocities. I'm guessing most of you don't know how to add, much less subtract, vectors. This is subtraction of vectors. So let's take just a few minutes to talk about how to add and subtract vectors so we can make sense of what's on this page. When I was in first grade, I was taught to add. I am actually the idiot in my family. I'm the only one that went to first grade out of 5 kids. How did your teachers teach you in first grade to add? Okay, your fingers. What did you say, Denford? With blocks?
You should be like the little dots on the numbers.
The dots in the number, okay.
Like where you stop and start with your pen.
Now we're getting to the way I learned. In my era, they didn't want you to count on your fingers. That was a crutch. They didn't want you to use the crutch. These days, they teach you a little differently. But Michaela is talking about what I learned. What I learned was how to add with a number line. So we had a number line, something that went like this. And we had 0 here, 1, 2, 3, 4, 5, 6, so on. And if I wanted to add 3 plus 2, Michaela, how do I add that with this?
You say 3 and then you say 1, 2.
Okay, so I start at 0 and I go 3. So there's my 3. And then to do the 2, I do what?
Just they have you point at it with your pen, so just 1, 2, stop. Start at the top. Start.
Okay, so that's still a little different than us. We actually drew these things. And so then I start at the end of the first one, and I draw the second one. So from 3, I'm going to count 2, so 1, 2. And so then 3 plus 2 is shockingly 5 because I ended at 5. Yeah, head mind blown. That's how I learned to add. And then my teachers went so far as to teach me to subtract. What's the difference in adding and subtracting? How would I do 3 minus 2? Okay, I would still go to the right 3, but then for the subtract, I go the opposite direction, so I would come back 1, 2, and I ended up at 1. And so 3 minus 2 is 1. That's exactly how we add vectors. We add vectors in what's called the tip to tail, or my high school teacher taught me tail to tip, method. You draw the first vector, and at the end of the first vector, you draw the second one. And then the answer, which we call a resultant, starts where you began, ends where you ended. So if I have these two vectors, and I wanted to add these two vectors, I would say v1 plus v2 can be graphically written as there's v1, there's v2, and so the solution when I add them together would be that. It's really a simple method to add, isn't it? Now the question is, how do we subtract? Because our equation here has a subtraction of vectors. When we did the number line, positives went to the right, negatives went to the left, right? Well, what we're going to do to subtract vectors is to reverse the direction of the arrow. So if I'm going to do vector 2 minus vector 1, v2 minus v1, that's going to be equal to v2 vector plus minus v1 vector. So now v2 vector went like this. That was v2. Oops, no, that was v1. Let's not erase. Too late. v1 went like this. So if that's v1, what should minus v1 look like? If it's minus, what's the opposite of going to the right? Going to the left. If it's minus, it's just going to be the opposite. So minus v1 goes like that. And so now I'm just going to add this minus v1 to v2, which v2 went like this. So v2 plus a negative v1 goes like that. And then how did I find my resultant? How did I find my answer? Went from what point, Tyler? Zach? My hand went to the next slide. It goes from, well, we added the two vectors tip to tail. And now our resultant goes from where we started to where we ended. And if I had done a really excellent job, that would have pointed straight down. And so that's v2 minus v1, which in our picture is pointing toward the center. So the acceleration is toward the center, just found by subtracting the two velocities. This here is a different way of showing the subtraction that I think is a little more confusing. It gets the same answer, just a little more confusing way of doing it. So just showing how we add vectors, we can see that the acceleration is, at this point, the velocity was that direction, or the average velocity throughout was that direction. The acceleration was perpendicular to the velocity when you're going in a circle. Long time to explain, actually, a simple concept. We've already seen this equation exactly, right? Acceleration, change in velocity over change in time. You can, of course, have an average acceleration and an instantaneous acceleration. For this class, all accelerations will be constant. Hence, average and instantaneous will be the same thing. The only case where it's not constant is when you're going a circle, when it's constantly toward the center. Okay, what is the acceleration in this picture that we started the day with? This is one-dimensional. It's going in one direction, so I'm only going to use without vector signs. What's the equation for acceleration? Okay, got two people telling me the change in velocity, change in speed if it's one-dimensional, over change in time. When I do change in, it's always which one minus which one? Final minus initial. So I'm going to put my final speed, 20 meters per second, minus my initial speed of 0. Notice I don't even need units if it's 0. 0 what? I don't care. It's 0. Divided by my change in time, which is final, 5 seconds, minus initial 0. Hopefully, everyone here is comfortable with saying, hey, 20 divided by 5 is 4. Now the units. If you look at this, you're going to want to say something like this. Meters per second divided by seconds. Right? Acceleration is the rate at which the speed is changing, so speed has units of meters per second, divided by time. And some people will indeed say meters per second per second. It's the change in meters per second each second. In physics, we tend to say, well, that's a silly way to say it or write it. It makes more sense to say this is equal to 4 meters per second squared. But then you ask, what in the world is a second squared? Right? There's no such thing is a second squared. Well, we're not talking about a thing as a second squared. We're just talking about the units. And this is distance per time, the speed, change per time. And so that's where we get the meters per second squared. So the unit of acceleration is meters per second squared. That's how we do the calculation. And it's time to go home. Well, go to your next class, I suppose. Don't necessarily go home.